Today I'm going to talk about some problems and their solutions in vector algebra, which is a branch of maths which has particularly many applications in 3D graphics and games development. The first exercise is I am at the point at coordinates 2, -3, which is somewhere here in the coordinate system, heading towards -6, 3, which is here. My speed is 2.5 units per second, and the question is what is my distance to the destination and what is my velocity. To calculate the distance, I need to know about the vector called destination displacement, d. It can be calculated using this simple formula, destination coordinates minus my current coordinates. So the destination displacement d is my destination coordinates -6, 3 minus my current position, which is 2, -3. Calculating this, you need to be particularly careful about using negative numbers. -6 minus 2, it's easy, it's -8. 3 minus -3 is the same thing as 3 plus 3, and this is 6. So our destination displacement is -8, 6. We will not use the graphical solution, so I will not read the solution from a drawing. This drawing actually is not to the scale, so only reading from this wouldn't be accurate. Graphical solutions are not applicable for computer-based applications, so we have to calculate everything, but still it's a good idea to compare the result, -8, 6, with this picture, 8 units to the left, 6 units to the top of the drawing, just for some verification of the result. This result looks reasonably good in this case. Once we have the destination displacement, our distance to the destination is nothing else but the length of this vector d. Here we have some useful formulas, and the length is shown here. Please note that in maths, names of vectors are marked with a small arrow on top of the letter. The length will show vertical lines. None of these markings are applicable for computers. For example, it would be very difficult to add a arrow on top of a letter. This is why my symbol is simply lower d for the distance to the destination. Okay, this is actually the length of the vector d, so it is square root of this coordinate -8 squared plus the second coordinate 6 squared. -8 squared is 64, not -64. Okay, it's 64 plus 36. It gives me a square root of 100, which is 10. So the first reply, the first answer we have is that the destination from my current position to the destination point is 10. To calculate the velocity, which is a vector value, unlike speed, I will act in two steps. Firstly, I will calculate the direction vector, which is the normalized vector, so it's simply normalized d. Normalized means that this black vector here, it's pointing in the same direction, so it's pointing in the direction of the destination, but its length is equal to 1. The formula for the normal vector is provided here. This is just the vector divided by its length. In our case, this is the destination displacement vector, this one, d, divided by its length, or the distance to the destination. So the direction vector dn, this is the d vector with an index n. This n just tells us that this is the normalized vector. This is just the symbol I am using here. It is equal my vector d divided by the length, the distance to the destination, lower d. So it's minus 86 divided by 10. The calculation is quite simple. That's the direction vector, which is pointing towards the destination, but its length is equal to 1. The velocity vector, shown here in the picture as the red one, the velocity vector is again pointing to the same direction as my destination, so it shows the direction of the motion, but the length of this vector corresponds to speed. This can be easily obtained by taking my direction vector, which is normalized, so its length is 1, multiplied by the speed, v in horizontal lines. That's the numerical value of the velocity. It's called speed. So my speed has been defined as 2.5 units per second, and my direction vector has been calculated here. So velocity is the result of this vector calculation, and after multiplications it's minus 2, 1.5. This value will be needed for the next exercise, so I will preserve this value of the vector for the second exercise, which is what will be my position in 10 seconds and what was my position 10 seconds ago. So I am still at the same position, 2, minus 3 here. I'm still heading towards the point minus 6, 3. Now I also know that my velocity vector is minus 2, 1.5. Okay? And the question is where I'm going to be in 10 seconds time, and also where I used to be 10 seconds ago. The assumption here is that the motion goes along the same line, so I don't turn left, don't turn right, and that the velocity is constant, so I don't accelerate, don't decelerate, don't turn anywhere. For the motion like this, we have a simple motion equation, which is shown here. The position in any given time t is my initial position plus vt, velocity, multiplied by time. Therefore, my position at time t equals to 10 seconds is given as follows. This symbols shows me means the position in the time equal to 10 seconds. That's the initial position p0, that's this one here, plus vt. Okay, so the initial position is basically 2 minus 3, plus velocity. Velocity is minus 2, 1.5. It was calculated in the previous step. And I also need the value of t, just to make this formula better looking. I put the time value here on the left side of this bracket. The time is 10. The question was about 10 seconds from now. At the moment, it is a simple vector calculation, so it equals to 2 minus 3, it's just copied. This vector has been multiplied by 10, so it's minus 20, 15. 2 plus minus 20 is minus 18. Minus 3 plus 15 is 12. Again, you have to be particularly careful about these calculations here, because you can have everything wrong, everything correct, and if you make a mistake with addition or subtraction which involves negative numbers, you can just get a slightly wrong result. Okay, position at time t equals -10 is the position 10 seconds ago. The same formula is applicable here, so this time this is the point for -10. The calculation is nearly the same. The only difference is that for the time, for t, we apply -10 number here, not 10, so the result is also different, 20 to -18. Here is the next problem to be solved. Are the points 0, 0 and 10 - 2 ahead or behind me? Let's imagine I'm flying in a spacecraft like this, and what lies ahead and what lies behind me is roughly easy to understand, but in mathematical problem, I have to provide a clear definition, and this definition in this case will be anything that is on one side of this black line here will be ahead of me, and anything on the other side is behind me. I also need a clear definition of what's my front, where is my front, and for this I will use the velocity vector, which has been calculated in one of the previous steps, and the assumption, maybe not always true, but in this case we will just assume that my front is always where the velocity vector is pointing. So that's my front. With these definitions, determining whether any point is ahead or behind me is just analyzing its relationship to the velocity vector. So it's the angle between the velocity vector v and this blue displacement vector for any particular point. If this angle is acute, like here, this means that the point is somewhere ahead of me. If this is an obtuse angle, like in this case, this is behind me. In this case, it's also an acute angle, so it's ahead of me, and most interesting case is the borderline case, where the vector is neither ahead or behind, it's exactly the right angle between my velocity and the displacement vector, so they are perpendicular. For this kind of analysis, we use normally dot product. Here are some formulas for the dot product, and what's interesting for us is this. If this is the condition for two vectors to be perpendicular, so that's the case of the displacement of this point, this vector and this. For these two vectors, the value of dot product is exactly 0. For anything which has an acute angle between velocity and the displacement, the dot product is positive, and for anything that has an obtuse angle here, the dot product will be negative. Therefore, this problem can be reduced to calculating the dot product of the velocity and the displacement vector for the given point, and if the result is a positive number, this means that the point is ahead of me. If it is the negative number, the point is behind me. Of course, if the dot product is exactly 0, this means that it's neither ahead or behind, but strictly on my left-hand side or my right-hand side, in the position which is perpendicular to my current velocity. So let's take the point 0, 0. Please note these are special coordinates. 0, 0, it's the point which is exactly here, but it's just a point like any other. So for the point 0, 0, the displacement of this point, which I will call here d1, again this 1 is just an index, this is a part of the name of this displacement vector. is calculated as destination. In this case, that's this point 0, 0, the point I am checking whether it is ahead or behind me, minus my current position. Therefore, oh, that's this green vector d1 here. So my d1, it's 0, 0, the coordinates of the point I am checking, minus my current position, 2 minus 3. 0 minus 2 is minus 2, 0 minus minus 3 is plus 3. So the displacement vector, the green one, is minus 2, 3. The next thing, and actually the last thing for this point, is to calculate the dot product. It's velocity dot displacement. So my velocity has been calculated previously. It's minus 2, 1.5 dot the displacement vector that I have just calculated. It's minus 2, 3. We'll take this formula for fast calculation, quick calculation of the dot product, which is x of one vector times x of the other vector plus y of one vector, y of the another vector. So this is minus 2 times minus 2, 2 x's, okay, plus 1.5 multiplied by 3. Minus 2 times minus 2, minus and minus gives plus, so it's 4, and 1.5 times 3 is 4.5, so the result is 8.5. 8.5 is a positive result, so the point is ahead of me. Now let's have a quick look at the point 10 minus 2. So the first step is to find the displacement. This is the second point we are analyzing here. So I'm using the d with index 2. Please note these are the coordinates of this point. So this is the point I am interested in, 10 minus 2, minus my current position 2 minus 3. The result is 8.8, 1. These are coordinates of the displacement vector of the second point, and the calculation for the dot product is here. The result is a negative number, minus 14.5, so the point is behind me. You can take any other point and repeat this calculation just for yourself. This is the last problem to be discussed in this presentation. Are the points minus 2, 2 and minus 2, minus 2 on the same or on different sides of my course? This problem is a little bit similar to the previous one, so once again let's assume that I'm flying a spacecraft, and what is on my left and what is on my right can be easily divided by this fat black line. As previously, I will use the velocity vector to define what is my front, and the velocity vector has been calculated in one of the previous steps. And now everything that is on the right of the velocity vector is my right hand side. Everything that is on the left hand side of the vector v is also on my left hand side. This displacement vector represents the borderline case in which the point is neither on my left or on my right, it's exactly in my front. To solve the problem, we will now use the cross product, which provides a condition for two vectors to be parallel. This is the case of this borderline case, which is exactly parallel to the vector of velocity, the vector v. For this case, the cross product is equal to 0. If it is greater than 0, this means that the blue vector is on the left hand side, and for negative value of the cross product, it's the right hand side. So what we need to do is to calculate the cross product of the velocity vector and the displacement vector for any point. and if both results for both points, this point and this point, have the same sign, this means that they are on the same side of my course, either left or right. But if one of them is positive and the other is negative, this means that they will be on different sides of my course. So, very similarly to the previous case, the first thing for these two, actually I have these points here, -2, 2, and -2, -2. The first thing to calculate is the displacement vector, in this case for the point -2, 2, this one. The name of this displacement vector is d3, this is the third displacement that we are calculating here, so the name contains the number 3. That's the coordinates of the point itself, -2, 2, minus my current coordinates 2, -3, and the result is -4, 5. -2 -2 is -4, that's correct, and 2 minus -3 is the same as 2 plus 3, it's 5, all correct. The cross product, velocity cross displacement, we'll be calculating using this formula here, without using this vector. It's just added for mathematical correctness, but what's practical, it's here in the brackets. So the calculation is as follows. You take the x of the vector number 1 multiplied by the y of the vector 2. It's easy to remember because we just take the externally lying values. -2 times 5. -2 times 5, it's here. Minus, it's not plus like in dot vector dot product it was plus, in cross product it's minus. Okay, so minus internal numbers, 1.5 times -4, it's here. The result is this will be -10, minus and minus gives plus, so it's -10 plus 6, it's -4. -4 means minus, if you take velocity first and displacement second in cross product calculation, the negative number actually shows the right hand side, but it's less important in this case. We just note that we have the negative number as the cross product number 1. How about the point -2 -2? For the point -2 -2, the displacement d4 is -2 -2 minus my current position 2 -3. The result is -2 -2 is -4, -2 plus 3 is 1. So that's the displacement for this vector here. And the cross product is here. You can double check this calculation, but the result is 4. Comparing both results, you can see that they are two different sides. We have one negative value, one positive value, so the conclusion is these are different sides of the course. Thank you very much.